Hey guys, welcome back. Today I'm going to be going over radicals and rational exponents. There is a lot of symbols and a lot of rules to cover. Some of the problems might look a little bit scary, but just bear with me, and if you have any trouble solving the problems, remember you can always go back and look at the rules and examples we had previously. So let's get into it. What is a radical expression? A radical expression is something like this. So you see we have this square root. This is the radical, and whatever is on the inside of the square root is called the radicand. And this whole thing is called a radical expression. Now, whenever we think about taking the square root of something, basically you want to say what squared equals g. And if you can figure that out, if you can figure out what this is right here, then you can know square root. Think of it like the radical. Okay, so the radical, it is saying some number is being raised to 1 over 2. So basically, a square root is the inverse in terms of the exponent. So basically what you're doing here is you're saying 1 over, and that's how we think of square roots. Now, square roots have something called the product rule, and basically this means that if you have the square root of two terms, you can actually separate them out. So the square root of a times b is the square root of a times the square root of b. And this works for numbers too. So say you have square root of 4. You can actually think of that as square root of 2 times square root of 2, because this is basically just square root of 2 times 2. So you can separate it out that way too. There are times where it may be two variables and you just separate it out like this. So let's look at an example real quick. We have square root of 75 n to the third power. Now, what you might notice here is 75 is a multiple of 25. So what we can do is we can separate out the 25. We can also separate out an n from the n cubed. We can have that. And basically what I'm doing here is you want to separate out perfect squares. So like square root of 25 is 5, because 5 times 5 equals 25. And the same goes for n squared. You're just putting your squares in one area, and then we'll take what we took out of those, which is 3n. And now we can evaluate the square root of these perfect squares. So what do we have? We have 5n times square root of 3n. 3n. And that is how you simplify that expression. Radicals also have a quotient rule. So say you have the square root of a over b. You can simply separate this out to the square root of a over the square root of b. Now, another neat thing, I'll show you this example. Say you have a coefficient in front of the radical. What can you do? Since these coefficients are both attached to the same radical expression, we can just simply add these terms together. It's like if you had 2x plus 3x. So this will give us 5 square roots of 5. The next thing we're going to learn about is rationalizing the denominators. So say you have square root of a over the square root of b. To rationalize the denominator, what you will do is take this and multiply it by the denominator over the denominator. So basically what we're doing here, we're allowed to do this because these terms cancel out, and this is actually just multiplying by 1. So this does not change the value of the square root of a over the square root of b if we multiply these out. So if you'll remember, for the numerator, the product rule allows us to combine the a and the b on top, and then anytime you multiply square root of something by the square root of something, the same radical expression, we can just get rid of the square root, and that becomes b. So that is how you rationalize the denominator. So what if on the bottom you have a normal number and a radical expression? Say something like 5 over 2 minus the square root of 6. How are we going to rationalize this? This is where you do something called multiplying by the conjugate. The conjugate is basically you have this beginning number, and then you want to flip the sign for the radical expression. So again, we're just multiplying by 1, but we have 2 plus square root of 6, the conjugate, over the conjugate. So what does this give us? Remember, it might be helpful if you put parentheses here. It just makes it a little more easy to take in. So for the top here, the numerator, we're going to be using the distributive property. So 5 times 2 is 10. And then we have plus 5 square roots of 6 over. And here is a good opportunity to introduce to you something called the FOIL method. This stands for first, outer, inner, last. So basically what you want to do here is you want to multiply the first term in each of the parentheses. Then you want to multiply the first term in the first by the last term in the second. These are the outer terms. Then you multiply the inner terms, and then you do your last terms. So what does this look like? This looks like your first, your 2 times your 2, your outers, your 2 times your positive square root of 6, gives us 2 square roots of 6. Your inners, it gives us minus 2 square roots of 6. You'll notice these cancel out. That's the power of using a conjugate. But now you multiply your last terms together. Remember, we can get rid of the square root, and don't forget your negative. So this will be minus 6. And now we rewrite. We have 10 plus 5 square roots of 6 over 4 minus 6, which is negative 2. You can go ahead and apply the negative to the whole expression here. And there you have it. That's how you use a conjugate. Now I want to introduce you to something called an nth root. So, nth root looks something like this. Basically, what we're saying here is we have a square root, but instead of a typical square root, which is something to the inverse of the second power, something to the 1/2, we can have a different number for the denominator here. So what does this look like? Looks like, say we have the 5th root of 7. So what's another way to write this? This is 7 to the 1/5 power. You can also think of it this way. So we have the nth root of a number to another exponent. Now, this is where you can have a different numerator. So this can be rewritten as a to the m over n. So say you have the 5th root of 7 squared. That would be 7 to the 2/5 power. Okay, so let's get into some examples. We have square root of 12 over 49, and we want to simplify this. So what I would do immediately is the quotient rule. Gives us the square root of 12 over the square root of 49. Then we can first, since this is a perfect square, let's just get that out of the way, write that as a 7. And then the 12, you'll notice that 12 is just 4 times 3. So like I said before, we can just use the product rule. This is square root of 3 times the square root of 4. And what we've done here, so we've separated out the square root of 4 because 4 is a perfect square. So what is this actually? This is 2 square roots of 3 over 7. Alright, just a couple more examples to go. So say we have, in parentheses, 25 L to the 3rd I squared to the 1/2 power. Now remember, the 1/2 is just It's just a square root. Nothing more, nothing less. So what we can do here is 25 becomes a 5. And now, using the power rule of exponents, we can multiply the 1/2 by the 3 and the 1/2 by the 2. So this gives us L 2 to 3/2 I just by itself. And that is already simplified. So for this last one, it is a bit scary looking. We want to continue to challenge ourselves a little bit. So say you have 62k to the 9th, in parentheses, raised to the 1/2 over 34k in parentheses to the 1/2. What I would do in this situation is I would separate out the coefficients, separate out the 62, separate out 34, 62 is going to be multiplied by k to whatever power. We are going to use the power rule. Go ahead and simplify this. So it will be k to the 9/2, and then this will be k to the 1/2. Now, I want you to notice something about these radical expressions here. So both of them are divisible by 2 on the inside. The radicand is divisible by 2. So what we can actually do is we can use the product rule. We can go ahead and pull out a square root of 2. It'll give us a square root of 31 on top. K to the 9/2. Pull out the square root of 2 on bottom. We're left with the square root of 17 there, times k to the 1/2. And now we just cancel out the square root of 2. Now let's use the quotient rule here. So we are going to subtract 1/2 from 9/2. We have the square root of 31 over the square root of 17. And this becomes k to the 8 over 2. Let's simplify that a bit. We have k to the 4th power. And now you want to rationalize the denominator. So what does that mean? That means we are multiplying by square root of 17 over square root of 17. Okay, so what does this look like? This looks like the square root of 31 times 17, which I did use a calculator to find this out, over 17, k to the 4th. And that's it. If you enjoyed this video, if you thought it was helpful, please drop a like, and I'll catch you in the next one.